diffusion operator with random jumps from the boundary. So
thank you very much. So thank you very much for the organization and for having invited me. So maybe those who know me a bit know that it's not, let's say, a typical topic on which I usually give talks, but anyway, there was some nice cooperation with a group in Prague. So and it seems that our impressions that it is potential of interest of what we managed to do. So I will try to tell you also a short story about this domain. So in fact, the whole story is about a class of differential operators with non-local boundary conditions. So here is the typical, the situation we are going to study. So we have a bounded connected smooth domain in RD, and we have a measure on omega. So, and with these two objects, with the domain and the measure, also which is supposed to be probability measure, it means that that's positive and the measure of omega is 1. So with these two objects, we associate the following operator. So for the moment, it's quite informal. I mean, I'm not specifying the domain. So, but it is just the Laplacian, but with a quite unusual boundary condition, so that at each point of the boundary, the value of the function coincides with the average, with the weighted average in the domain. So for the moment, I mean, it's informal. I will specify, I will say some words about the domain, because in fact, somehow there is no unique approach. There are several approaches. So in principle, I'm just writing the Laplacian just to have a shorter writing. In fact, instead of the Laplacian, one can consider something more general. So in fact, somehow it is a bit mysterious that it is not, somehow this expression is not as important as one could expect. Somehow it can be replaced by more general elliptic differential expressions. But what makes this whole story complicated is that we have this non-local boundary condition involving a measure. And I'm going to discuss the following questions. So first, how to define this operator strictly, so that one obtains an operator within a reasonable class in the Hilbert setting. And then I would like to say several words about spectral properties of this operator H. So I say in advance that somehow the spectral theory of this operator does not seem to be complete. So there are some, let's say, partial results, but anyway, I mean, nobody understands the general picture, picture in full. Yeah, so I mean, nobody understands the full spectral picture, but I'm trying to understand what so I will try to tell you what we have managed to understand. So of course, the operator was not introduced by us. So maybe it seems that it was at least the earliest papers about this operator we know were due to by Ben-Ari and Pinsky. So almost 15 years ago. And then there were some other development by Arendt, Kurkel, and Kunze 5 years ago. In fact, Ben-Ari and Pinsky, they discussed the operator in the following setting. So it's models rather special Brownian motion in omega. So you have, let's say, particles moving inside omega, but as soon as the particle touches the boundary, if the particles hit the boundary, they are sent back to omega. And the distribution is according to the measure mu. So mu is actually, in fact, the probability of that the particle will be in some region A, it will be mu of A. I mean, just if you, let's say, if your particle is here, then it's sent back to omega. and the probability that the particle is in this region, it's exactly mu of A. So this is, let's say, somehow the interpretation which was proposed by Ben-Ari and Pinsky, and somehow there are some theorems in this direction. So that this interpretation, so if suitably formulated, is really holds. Yeah, but then the question is in which space you are supposed to study this operator. So, in fact, I believe that the most complete study, it was due to Arendt, Kurkel, and Kunze. So, in what concerns the strict definition of the operator, but they defined this operator in the in a quite which is in a quite unusual space, which seems to be natural for the diffusion problems, but looks quite exotic for personally for me. This is a continuous functions with an additional Sobolev regularity. And they have shown that, okay, this operator has nice properties, but these are the evolution people. So they have shown that the operator A, which is literally defined as here, but just on the domain, now on the very specific domain, on the special domain, just sorry. Okay, here. Then it generates a contraction semi-group with some additional properties, and it follows. In fact, from the fact that it generates a contraction semi-group, it follows that all eigenvalues of the operator, which are non-zero, have a positive, strictly positive real part. And moreover, in fact, in this story, there is, in fact, a constant which is of interest, this is the following constant gamma. In fact, you take all eigenvalues which are non-zero, and then you take the infimum of their real parts. And in fact, it can be shown that this number is positive. And as soon as you have this constant, you may show the following thing, that if you have the semi-group which is generated by A, then for any initial data, this semi-group converges very rapidly to the function which is constant on the domain, but then we'll multiply it by, let's say, multiplied by some constant, which is actually quite reasonable usual property for the diffusion processes, that it converges to the equilibrium. And in fact, this constant is participating in this in the speed convergence, the speed of convergence, and so it means that it's somehow of importance. But in addition, sorry, there is something stupid here. In fact, there is in the earlier papers, there was the following question: is this number itself an eigenvalue of the operator, or it can be reformulated so equivalently? Do we have an eigenvalue with the smallest real part, and if such an eigenvalue exists, if it is real? Because in fact, one can easily show that the operator is somehow real valued. So it is, I mean, if there is, so in fact, there are some very easy things. For example, one is the obvious eigenfunction for the eigenvalue 0, because the function which is everywhere 1 obviously satisfies this condition, and HU is then 0. So, and in fact, if one assumes that okay, this constant is an eigenvalue of the operator, then the estimate of the convergence can be, in fact, not this estimate. I mean, this convergence can be actually improved. In fact, one can write additional terms here, and then a better speed of convergence, because somehow it converges to the constant, but then one can find a kind of next term, which is somehow the limiting profile. It would be the eigenfunction for gamma. And in fact, it was our side of the question. This was something we tried to understand, whether under which conditions it can be shown that this that this number is an eigenvalue of A, or at least if we do not manage to show that this number is an eigenvalue, can we in fact estimate this constant using some let's say using some information on the domain and on the measure. Because in this story, we have a geometric object, which is a domain, and so an additional analytic object, which is a measure. In fact, if one looks through the literature, that the answer to this question is known to be yes for several special cases. First, it happens to be true in the dimension in one dimension, and which looks a bit confusing because but somehow it's easy to show that it does not hold. In fact, in one dimension, the situation is quite weird. The operator is clearly non-self-adjoint. It can be shown somehow. In fact, it can be shown directly that it is not self-adjoint. But anyway, the eigenvalues are real for any measure, and in fact, without any additional assumption. But in dimensions two, in fact, it is also shown that at least in two special cases, all eigenvalues are real as well. But this, but in fact, if you just look at these two special cases, it's not clear at all why, what is the role of these cases, but we will, I hope it will be clear. So if you manage to follow my talk, you will see that somehow these measures are very natural from the point of view of the spectral analysis. So the first of them is probably the simplest one, is just the measure with a uniform density inside omega. And second is the second case, it's you just take the first Dirichlet eigenfunction, which is so normalize it as usual. So and then you normalize to 1 in L1. Okay, then it's clearly a probability measure. In these cases, all eigenvalues happen to be real. So just let me recall that the problem we are studying is written here. Yeah, but anyway, there are examples in two dimensions such that there are complex eigenvalues as well. So it's but anyway, this does not answer this question, because somehow the complex eigenvalues which were found in some particular situations, they do not correspond to the lowest eigenvalue. So the question is still open and somehow in higher dimensions. So, but anyway, later I will try to show to explain why, let's say, because in fact the proof for the one-dimensional case, it's a bit it's really funny, and in fact it's so implicitly it was proven 100 years ago, even before this operator appeared. Okay, so what did we do in this direction? So as we are going to work in the L2 setting, so somehow all collaborators are mostly Hilbert people. So we were trying to understand how to deal with this operator in the Hilbert setting, because in the Hilbert setting you have some, let's say, additional machinery which is absent in the Banach setting. So why not trying to do something with with the Hilbert machinery. So, but to deal with reasonably defined operators, we need an additional assumption. So, namely, we assume that this map is unbounded, is bounded on H2. So, what in fact what are admissible measures? Admissible measures, these are of course something like absolutely continuous measures. It's so with reasonable weights. Or it can be something like, let's say, delta interaction supported by hypersurface. It can be shown. So, but somehow not all measures are allowed. For example, point measures like delta function in higher dimension would not work because it is not bounded. Okay. So, and then we consider our operator in L2 omega. And in fact, it's the same H, except that now we assume that the function U is that the domain of this operator is explicitly given. This H2 function U, which satisfies the same boundary condition. So one can show, and in fact, it's not completely obvious, but anyway, not that complicated, is that this operator is densely defined. One can also show that it is not essentially self-adjoint. So a bit mysterious thing is the following thing is that the numerical range of this operator is C. So what is the numerical range? In fact, you just consider all possible scalar products, so H psi in L2 functions which are in the domain with which are L2 normalized, and in fact it appears that the numerical range is a whole complex plane. But in fact, so in particular, it's not something like accretive or something like this. And all these properties fail very quickly. But anyway, for what can be done for the eigen, so in fact, lambda is a simple eigenvalue with eigenfunction, which is identically 1, and all other eigenvalues are with a strictly positive real part.
Sorry, Konstantin.
Yes.
So is the spectrum consisting of eigenvalues only?
No, in fact, in general, we do not know. We cannot. We can and say under some additional assumption, yes. But I will say so. So thank you. It's an important point. But I mean, in general, we do not know if the spectrum is the eigenvalues. We do not know, but we know it. But I say in advance, we know it for absolutely continuous measure. I mean, if mu is let's say absolutely continuous, then yes, it's true. But in general, we do not know. But to be honest, we did not try that hard in this direction, so maybe it can be improved. But anyway, somehow it does not follow from any. We did not find any suitable argument which gives it immediately, because it's required some work, in fact. So I mean, if the measure is absolutely continuous, then the spectrum only consists of the eigenvalues, and there is a kind of completeness of root vectors. But in general, for general measures, we do not know. Let's say, okay, this is the honest answer. So, and then what again? So back to this constant gamma. So what can we say about this constant? So we were not able to deal with this problem as a full generality, but anyway, we made some contributions. But in this contribution, we will use, okay, we need the Dirichlet eigenpairs of the domain. So I take, so let lambda j be the Dirichlet eigenvectors and eigenvalues, and psi j will be L2 normalized, the L2 normalized eigenfunctions. So the first case is when we take this uniform measure and we perturb it by absolutely continuous measure with a L2 weight. But anyway, there are some, in fact, there are some hidden assumptions that this should be still a probability measure. It means that this V should be somehow not very negative, so that the whole function should be non-negative. So, and if we have this approximation, so if we have this inequality, so the norm of the V square, so the L square of the L2 norm of V is smaller than something which is determined by this spectral data, then, so in fact, the result consists of two parts. So first, H has no, in fact, this assumption depends on the number K. So then H, so it somehow should suppose it to be small compared with the first J, eigenfunctions, or with first K Dirichlet eigenfunctions. Then it can be shown that H has no non-real eigenvalues in the domain. Okay, just let me show here. no real eigenvalue. So in this in some so half plane first, and then in addition, one can show that if lambda if in fact this the eigenvalue lambda k is non-degenerate, then in fact there is at least one real eigenvalue in this region, and it means that the eigenvalue there exists an eigenvalue with the smallest real part, and this eigenvalue is then real. So in fact, in the first part we show that in this half plane there are no all eigenvalues, if any, are real. But then we show that if these two numbers, so lambda k and lambda k plus 1, are not the same, then okay, this looks very mysterious. It's a condition, but this is what we can do. But then in this region there is at least one real eigenvalue, and then this eigenvalue, I mean, that means all non-real eigenvalues, they are here. It means that the eigenvalues with the smallest real part would exist. Anyway, well, okay, in fact, one could say that it's kind of, let's say, perturbation result, but with explicit constants. But, okay, but in effect, this condition is not as good as one could expect, because, for example, if if your domain is symmetric, let's say if you are on the rectangle, then on the rectangle, let's say the second eigenfunction is 0. Or no, not non-zero, but it says somehow the average value is 0. I mean, for example, for the rectangle, this condition does not bring anything because this integral is 0. For example, and the same for the circle. So it's a kind of, but I would say so. One can certainly, I mean, for general domains, this psi2 is certainly not 0. But it's a bit frustrating that for, let's say, for all domains, you can, so like, I don't know, so like say rectangles, or let's say annulus or something like this. I mean, this condition is not satisfied. Yeah, but as I said, it doesn't supposed to be optimal, just to try some approaches, to test some approaches. And the second case is when we perturb, okay, the first, so the ground state, the ground Dirichlet state, again by an absolutely continuous measures. In fact, properly it must be with dx, in fact. And again, so then if somehow the perturbation is somehow suitably small, then we just show some localization of eigenvalues in some special region, in a region of a rather specific shape. So in fact, it does not prove that this constant gamma we are interested in is an eigenvalue. So we do not know, it does not mean anything in this direction, but anyway, it gives some estimate for this constant. So, and in fact, this is a bit easier because here there are no symmetries. So again, and somehow it's really, the objective of the work was just really to test some approaches on this problem, because so far only very few results were available, and moreover the problem does not seem to be very well known to the community. So my talk is somehow also a contribution in this direction. I will try to popularize the problem. But just I would like now to give some proof ideas, and in fact, but because it's really, so in fact, if you just look at this operator for the first time, you really have no idea how to deal with it. But somehow it's really very instructive, let's say, to understand the proof that the eigenvalue, all eigenvalues are real for one dimension. So assume that we are in one dimension. So, but then, so without loss of generality, let us assume that our omega is just the interval 0, 1. So what do we want to know? In fact, it's somehow extracted from a paper by Leung, Lee, and Rakesh from Proceedings of AMS 2008. So in fact, so in one dimension, so you consider just directly the eigenvalue problem. Okay, for technical reason, as usual, for one dimension, I denote my eigenvalue as k squared with a complex k. So I need to solve this differential equation with this boundary condition. So first if in fact we start by let's say forget first this condition and just consider okay this so ordinary differential equation with okay, so functions will look for solutions which have the same values in 0 and in 1. So after some trivial computations, you show that all these solutions are constant and then the difference of two sine functions. So it's rather usual computation. But now we use the integral condition. So we put this function into this integral, and then we obtain the following condition for k. So then this can be further simplified using some simple trigonometric formulas. So this is this product and the expression in this product. In fact, this is still very generic because we integrate with respect to an arbitrary measure. In fact, so it's very, but it's important. This is a probability measure. This is really important. So, but now, okay, we see that there is this factor sine of k over 2. So, I mean, so if this factor is 0, then of course we have the equality, but the corresponding k's are real, and this would give so real eigenvalues. And moreover, suppose not just, in fact, eigenvalues are not just real, but they are in fact positive. This is the point. It's positive. So, but if it is not, if this condition is not satisfied, then the two other terms must coincide, and then we obtain this condition for k. So in here there is a rather obvious trick. So with the help, so you can, in fact, we use the integration by parts for Stieltjes integrals. So for this we consider the function f of x, which is mu of 0x. Which is then somehow left continuous and so on. And then we can show that we can integrate by parts. So this gives the cosine of k over 2, and then an integral in which there is no measure at all. In fact, then you simply have the usual Riemann integral. Or better to say it's a Lebesgue integral because the function is monotone, so it's measurable. But anyway, it's yeah, okay. So it means that the condition for k finally takes the following form. So there are no measures at all. The measure is encoded in this function f. But then we further so decompose this sine into sine cosine, so on. So and we obtain the following linear combination. So this linear combination yeah, must be yeah, okay, must be 0. Yeah, okay, and then in fact okay, this is something here. Oops, sorry, just no, so what is written here, it's not okay. Anyway, somehow there are just, I'm sorry, this is not written in a reasonable way, but anyway, it's then in fact there was a paper by rather known paper by Pola, so in 1918, which in fact deal with these integrals. So in fact it's a bit more involved with what is called. Sorry. In fact, they have shown that if the function f is non-negative, non-negative, non-decreasing, and not identically 0, then these functions cannot have can only have real zeros, and not only these functions, but also if you multiply them by some reasonable functions. And in fact, what is written here, it's exactly the expression. In fact, what the expression which is written here is exactly in this class, because it really looks mysterious that somehow you obtain the same expression as what is written in that paper. Yeah, okay. And in fact, but in fact, what is in fact, I cited the paper by these two guys. In fact, the result holds even if you these two measures. I mean, instead of this boundary condition, in fact you can write two conditions: u d mu 0, 0, it's integral u x d mu 1 of x. And in fact, even in this more general case, all eigenvalues are real. It's somehow really mysterious and just okay. But so it means that in fact, the only possible values are values of k which are admissible are real, and then the eigenvalues are positive. So it's a bit, but this result is somehow not for free. I mean, somehow it needs. It's not very complicated, but I would even say that I do not know any reasonable source in which it is written with sufficient details. But okay. Yeah. So, but okay, let us now. But of course, this proof used heavily as the one-dimensional nature of the problem. But okay, what happens in arbitrary dimensions? So, in fact, if you look carefully at the definition of the operator, you just see that if you are in the domain, then the function u is constant on the boundary. And it means that as soon as you remove the boundary or remove this constant, in fact, you may decompose it into a constant plus something which vanishes at the boundary. In fact, it shows that the operator H is just, in a sense, it's something very simple. It's just a rank 1 perturbation of the Dirichlet Laplacian. But I mean, but anyway, it's a non-self-adjoint rank 1 perturbation. So, but anyway, for rank 1 perturbation, there is some, let's say, okay, there is some understanding of how to deal with them. In particular, so with some reasonable efforts, one can show the solvent resolvent formula. So you can compare the resolvent of the operator with the resolvent of the Dirichlet Laplacian. And the formula looks like, so it's in fact written here. So this is some rank 1 operator, which looks a bit complicated, but anyway, it's a rank 1 operator. And then this term with a scalar function m. So, and the scalar function m, okay, this lambda m lambda, and then this function m, this is in fact something rather which looks not that complicated, I would say. So it looks as following. This is the resolvent. You take the resolvent of the Dirichlet Laplacian, you act on the function which is 1, and then you integrate this function with respect to the measure through the whole domain. But or equivalently, you can rewrite it through. So if you take, so this is known to be an integral operator. It's integral kernel, or let's say green function. Then you can rewrite the same function as this double integral. So, and in fact, one can show the following, that if lambda is not in the spectrum of the Dirichlet Laplacian, and if it is not 0, then it is eigenvalue of our operator. Then, in fact, the condition to be an eigenvalue of H and is the same as the condition to be a 0 of the function m. So yeah, yeah, okay. Yeah, okay, yes. Because here there is lambda, so which gives the eigenvalue 0 with a constant eigenfunction. So it's a kind of, let's say, Biermann-Schwinger principle for this particular situation. So, but in fact, one understands the problem much better if one uses the spectral representation of the Dirichlet Laplacian. So if one uses it, then we obtain the following series representation for the function m. So in here we see in fact the problem. So here we have so sum of products, but there are two terms. But in first of them we integrate with respect to mu, and the second of them we integrate with respect to the Lebesgue measure. But okay, this is the usual series representation. And in fact, now the role of the, let's say, of the uniform measure becomes much more clear, because if mu is a uniform measure, then in fact, these are the same numbers. In particular, they are, I mean, if the eigenfunctions are chosen as usual real valued, then this number is positive. So, I mean, this number is then positive, or let's say non-negative, let's say, and in particular, the imaginary part of M. In fact, this is a so-called Helmholtz function, and as Helmholtz functions, they only can have real zeros, because if you take the imaginary part of it, you can show that for if imaginary part of lambda is non-zero, then say of lambda is zero, then the imaginary part of the function is non-zero as well. And on the other hand, if you take, let's say, so if you take mu, the ground state, Dirichlet ground state, then M of lambda is something very easy, and of course, but in fact, it then has no zero at all. I mean, then it's it means that the spectrum, the whole spectrum, is contained in the Dirichlet spectrum unified with zero. So. But in fact, all existing, in fact, I would say this is the only result for the high dimensions. I mean, this series representation on which basis everything was proved. That in fact, so this M lambda is, so you have either this series representation or this integral representation, depending on so what you prefer, and then everything, in fact, then you need to study the zeros of the function M of lambda. And actually, this explains why the problem is complicated. But let's say one could imagine that under some conditions, one manages to show that all zeros are real. There are many theorems in this direction, but it's not clear how to show. In fact, we are not aware of any result that guarantees that just a specific zero is real. I mean, this is somehow we are not aware of any result in this direction. So, but in fact, it's rather funny that in that paper by Pola, in fact, at the beginning he said that so between the line you can recognize that somehow his intention was to prove the Riemann conjecture, but finally that somehow the assumptions are not satisfied for the Riemann, so for the Riemann zeta function, but he produced it. But anyway, this paper is very well known. I mean, the paper is really, I mean, it's about zeros of the functions of this form. I mean, sine z of x, or with various, let's say various. We integrate 0 infinity or 0 1, and somehow they produce the paper contains a number of results which are actually very elementary. I mean, if you, let's say, look for topics for bachelor students, it would be a good one, except that the bachelor students should be able to read in German, because the paper is in German. Yeah. So okay, and yeah. Yeah, okay. This is, but anyway, this I hope so. Maybe I hope that someone managed to follow my talk up to this point. So okay, but what can we say under additional assumptions that the measure is absolutely continuous with L2 weights? In fact, it's but for example, under this assumption, we can compute the adjoint operator for H, which then looks. Okay, is expected. It's then a real, so a nice rank 1 perturbation of the Dirichlet Laplacian. This is really specifically, I mean, this is just Dirichlet Laplacian plus something of rank 1. And then, in fact, by applying some results from Buch by so-called Gorberg and Crane. So I'm sorry. I'm very sorry. So, in fact, by citing suitable results, the fact that you manage to compute the adjoint, which is then densely defined and so on, it shows that the system of root vectors of H and then of the adjoint are complete in L2. And in particular, it implies, what I mentioned at the beginning, that the spectrum consists of infinitely many isolated eigenvalues which accumulate to complex infinity. So, but let us continue with such mu, okay, which are absolutely continuous with L2 weights. Then, in fact, the central condition that m of lambda is 0 and lambda is non-real implies, okay, this can be weakened a bit, that then it implies some other identity which involves the resolvence of the Dirichlet Laplacian and the weight. So, and in fact, one can exclude non-real eigenvalues in some regions by showing that this equality is not possible. But maybe I will just mention one of the steps. Okay. So what happens? For example, what happens if we perturb the uniform measure by an L2 weight? So if we assume, as I said, that the weight is small in a suitable sense with respect to the first k Dirichlet eigenfunctions. So when we consider this half plane, each k, which are lambda k plus 1, and then so on. So in fact, so if we now just inject this representation of mu into this necessary condition to be an eigenvalue, to be a non-real eigenvalue, then in fact it can be rewritten in such a way. But then if you use the Cauchy-Schwarz, you obtain an inequality between the action of the resolvent on the V, on the perturbation, and the action of the resolvent on the constant function. Yeah, but then in fact you show that it is not possible because I mean you use some clever estimates for the norms. Just a moment, maybe square. So using the usual series representation, so somehow, this passage is maybe non-obvious, but it's elementary. And at some point, in fact, you just need just show that the maximum of this expression for lambda, if lambda in this half plane is the same as maximum over the first k eigenvalues. So in effect, then you may show that somehow you have a contradiction because you obtain two opposite inequalities. So the existence of real eigenvalues below. Let's show how to. So we have shown that in some region there are no non-real eigenvalues, but what about real eigenvalues? So in fact. Let us just discuss the case when all eigenvalues are simple, just to make it, because somehow it simplifies the whole discussion. Then, in fact, we just choose the interval lambda j plus 1. Then one can simply show that it has the following representation, which is this is two poles and then plus something continuous. And it is important that the residues are positive, so it means that somehow by the intermediate value theorem, in such an interval, there is always a real zero of this function. So somehow it's this is somehow it's very elementary, but this makes the things are really complicated. But okay, I will probably not discuss the second case, but anyway, the second case is again based on the, let's say, on the representation of this M. Somehow you need to switch at several places, let's say switch between series representation and somehow some resolvent representation. I mean, so if you perturb the ground state, then you can show some enclosure for the eigenvalues. Okay, maybe I will remove it, but I'm not going to discuss it. But then I would like to, in fact, just mention another proof, which I also find very funny. And if I think it deserves to be known, and somehow it doesn't seem to be in the literature. In fact, it seems that in fact it was in fact Sergei Denisov who indicated that this way of proof. It's just again for our operator H, how can one show without any semi-group argument that all eigenvalues have positive real parts? Because as I said, it's not its numerical range is the whole plane. I mean, so its accretivity cannot be used at all. I mean, so it's and this is in fact this is a very nice argument. And again, it does not use any semi-group theory. Again, we just need to show that okay, all zeros of this function m of lambda, all zeros lambda are these positive real parts. And then it's here there is a clever use of the heat kernel. This is actually something very superposition of various topics. But in fact, if you represent again what was here the function, it was the green function of the integral kernel of the resolvent of the Dirichlet Laplacian. But you can represent it as using the heat kernel, using the usual Laplace transform. And then this function whose zeros are of interest, so is just the Laplace transform of some function f. And the function f is written here. But then we represent this function f in an additional form. This is somehow the average value of u of xt, and u of xt. This is something which involves the integral of the heat kernel with respect to the measure in question. And the observation, this is really the key point, that this is nothing but this function solves the heat equation, because the heat kernel solves the heat equation, and with the Dirichlet boundary condition. So, and an important point that the heat kernel is positive. In fact, it's a positive function. And that means that if you, again, we are interested in the zeros of this function m of lambda, and what can be said about the function f, which is in fact this function. In fact, we can, let us just compute the derivative of s with respect to t. Okay, we just then put the derivative inside the integral. Then we use the heat equation. So here we use the divergent theorem. So we must integrate over the boundary of the domain, the normal derivative, but the normal derivative cannot be positive because the function is 0 on the boundary and it is positive inside the boundary. It's a sin, it's clearly sin, but this function is positive because you integrate positive function with respect to probability measure. And therefore, so the whole thing is non-positive because this is an exterior normal derivative. It means that the function f is non-decreasing and it goes to 0 because again it's a pointwise estimate for the heat kernel. And then there is another nice theorem by Polar as usual. So it says that if you have a function which monotonically goes to 0, then there are no positive k such that this integral is 0. So this integral is 0, which is actually almost trivial because somehow you split it into the periods of sine and then show that somehow it's quite elementary. And then we want to show that finally that m of lambda cannot be 0 if the real part is non-negative. So let us take lambda and represent it as the usual way with, let's say, mu is non-positive and k, let's say, to be definite, let it be positive. We compute the imaginary part of lambda, and this has this nice form. So we have a function which goes to 0, and it means this function can only be 0. I mean, if the function is 0, then the imaginary part is 0, but then by Polar result, the k should be 0. But then all complex stuff disappears and we obtain m of lambda. This should be 0, but this cannot be 0 because it's positive. I mean, it's just because again, we have a positive function which we integrate. So as you see, this is really at the crossroad of somehow an incredible, so far it's a really incredible mixture of topics, ranging from, wave equation and Dirichlet Laplacian and so non-self-adjoint operators and some Brownian motion. So it was a kind of first attempt to understand something from the Hilbert point of view. And as I said, my objective was merely to just to attract, to draw your attention to this, to this problem, because it seems that the problem was not given an amount of attention it should attract. It should attract, in fact, because the problem looks really very classical, but so far there are only episodic papers by my impression. At some point, I would say non-specialized people. So if you have ideas, and in fact, it can be reduced to a very simple question of zeros for some integral which involves the heat kernel or the green function. So what you prefer. So and I thank you all for your attention.
Thank you very much, Konstantin. So there is room for a few questions. So
may I?
Yes, Pavel.
Kostya, comes to mind, would or could something like that work in case omega is unbounded? I mean,
yeah, but what do you mean exactly? I mean, for unbounded, but in fact, there are papers showing that for some unbounded domains, it also generates some kind of semi-group. But I'm afraid I'm not. I would not expect. Concerning the spectrum, I'm not sure that I'm able to do it, because, for example, this proof of what is written here, it would not work because simply the heat kernel would not go to zero. Somehow, I mean, so let's say if you have a bound, let's say, I would say if you have a positive Dirichlet eigenvalue, first eigenvalue, Dirichlet eigenvalue is positive, then this could probably bring something, but in general, if you take something like half space, for example, I would say this proof fails. I mean, it doesn't mean that the result is not is wrong, but I mean, this proof would.
Well, if you have a cube or something like that, or.
Yeah, but I said the problem is that cubes. I mean, this is something where the symmetries are dangerous. I mean, as I said, because the conditions we have written, they all fail for cubes and balls. I mean, which is a bit frustrating. But I mean, so far it's just really an attempt to do something, just to understand how to deal with such operators.
Okay, thank you.
Okay, other questions?
Yeah, it's Nicolas from Lyon again. It's concerning just the starting point. You said so it's a model for you have a Brownian motion in the domain, then the particle hits the boundary and it's sent at random in the bulk. Has it been looked into what a model where the place where you are sent back in the bulk depends on the place where you have hit the boundary?
Yeah, okay, this is true. In fact, yeah, I mean, in fact, those guys, in fact, those guys, they in fact studied the more general case, so they have shown that E of mu of x is equal to omega u, and then the measure also depends on x. And in fact, also, I think in one of these papers, they also, no, I'm not sure. No, I think it's no. I think those people, they consider the fixed measure only. But I would say it's very base. But I mean, also in this case, they have shown that, I mean, all these results, they are valid in this case. But of course, you need to assume that the measures on the boundary, they are somehow regular with respect to the point on the boundary. So it exists. I mean, the results of this type exist. And of course, you are not obliged to consider you can be even more general than what I have written here. You can add some first order terms, and but then you need to change the measure in your domain. I mean, that's
okay.
I mean, it's really somehow the nature of these properties is not clear at all. I mean, but yes, I mean, it's but it. To be honest, it was for us with several measures. The problem for us was too complicated.
Yeah, sure. I understand from a mathematical point of view, you want to start from the simplest. Yeah, so I'm just curious whether the question made sense. And okay.
Yeah, but right. Okay. But to be honest, I'm not, let's say, really specialist in this domain. So in fact, everything I would say this. I would say let's say 4 papers I cited here. This is the only papers I know on the topic. So I mean.
Okay. Thanks.
Mhm.
And speaking about measures, could you say something particles in case when mu is a point measure?
Say no. In fact, the point measure was used to produce a counterexample. I mean, it's by, I do not remember by whom it was. In fact, they considered sorry, just a moment. In fact, if you consider, let's say, the ball, or yeah, I mean, it's the ball. I mean, if you put your mu is delta, which is placed in a some, let's say, somewhere not in the middle, then it can be shown that there are non-real eigenvalues. I mean, this is, but I would say this is the only observation I know about delta measures. I mean, so in fact, this is the only counterexample with non-real eigenvalues, because as I said, in one dimension, it's always real and positive, and okay, that's all.
And if it is in the center, it's basically one-dimensional because you can.
Yeah, but in the center, yeah, it produces only real eigenvalues. Yeah, but anyway, this is, I mean, it's not just. It must be placed somehow intelligently, because it's not somehow. It doesn't mean that you put it somewhere and it immediately produces some non-zero eigenvalue. Somehow there is a configuration of such a type with a non-real eigenvalues. This is there is such an observation.
Okay, thanks.
In fact, we tried to study just the rectangle. I mean, if that's all, let's say a rectangle, but by taking, let's say, just a linear combination of, let's say, some 2 or 3. In fact, it is known that if you take just a linear combination of 2 eigenfunctions, that only eigenvalues are still positive, which looks. But let's say we have tried with 3, but we did not succeed, because somehow in all cases we just. In fact, it's already technically difficult, because you need to check that this linear combination is still positive, which is not that easy. But anyway, somehow we tried to find, let's say, the case where the lowest eigenvalue is non-real, but it didn't work. In fact, finally, because somehow in all cases, because it seems that there is something really very deep that nobody understands so far.
Okay, so other questions? So probably not. So I just have a small question about disk domains. Was it possible to do, have you tried to do change of variables, tricks, and so on to find the spectrum? Or?
No, just to be honest, no. I mean, no. The main perturbation result and so on, it's no, I simply no, we didn't try.
Okay.
In fact, you can write a kind of quadratic form here, it's true, but anyway, it's as it's non-self-adjoint, it's very easy. So it's difficult to deal with. I mean, okay, that's just okay. The answer is no, we didn't try. This is my answer.
Okay, thank you. So thanks again, Konstantin. So